Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics 1. This lecture is entitled the VHDL Architecture Statement. So if we remember correctly, the VHDL entity statement was a description of the factory's inputs and outputs from the external view. What is the architecture statement? What it is, it's the internal workings of the factory. Basically, what do you do with those inputs to make an output? So the architecture statement, it's despite all its potential complexity, your ability to do some crazy things with those inputs, to have some crazy outputs, structure is actually a little bit simpler than even the entity. What I'm going to do is just write out the general format. Architecture, and I'm going to put a little blank space right here, of, another blank space, is. And then I'm going to leave a conspicuous space right here. We're going to come back to that thing in between. I'm going to say begin, then I'm going to say end with another blank space and close the whole thing up. And that's the general format of an architecture statement. Okay, it's pretty simple. And what goes in these blank spaces? The things in yellow and the things in pink. The two things in yellow need to match up. What it's describing is, and just think of the thing in pink, that's the name. The architecture of Happy Cat, cat food factory. That's how Happy Cat behaves. This thing in yellow, no one has ever given me a satisfactory explanation of what that thing in yellow is. I guess my description of it is how you're performing the Happy Cat architecture. You could call it the behavioral description of Happy Cat. You could call it the SOP, sum of products method. So you'd have to change if I called that the SOP implementation of Happy Cat. I could just call it generally ARC, ending that type of description of Happy Cat. As long as these two things match, that's all that matters. Skipping over this section here. We'll come back to that. Between begin and end, that's where you put your logical statements. Right now we're dealing strict with the logical statements for these things. We can go into behavioral descriptions a little bit later, some loops in there, keeping it real simple right now. This is where you put in the logical description of how the thing behaves. And for our example 1 is our Happy Cat cat food factory. Someone has given you the logical expression. Someone has given you the logical expression. We will go into how to develop a logical expression based upon desired outcomes given certain incomes and truth tables. We'll go about that. Someone has given you this expression. They say that your cat food, it's equal to cat food when there's either seals and corn husks, or when there's seals and ground up gym mats. Okay, because we want our cats to have enough fiber. They've got to have some filler agent in there. We want them to have enough protein, so we've got to make sure at least seals in there. What if you happen to have seals and husks and mats? Yeah, you still got cat food because you've got a filler agent and protein. I know this is a disgusting example, but you'll remember. I guarantee you'll remember this one. How do we write that in VHDL? What I'm asking you to do is take that logical expression, put it in there. Okay, so you know the AND operator, you know the OR operators, and one would think, notice how I've written this thing here. I don't have parentheses in it because I know multiplication occurs before addition, logical multiplication before logical addition, basically ANDs before ORs. Does VHDL know that? And I was going to kind of wait till lab to actually do this, but since this is kind of going out for broader dissemination, I don't want any misconceptions to start when you're programming VHDL. Let you run into errors, okay? And you will run into errors. I guarantee you'll run into errors with this. These syntax errors. Syntax, like I said, is grammar. It's kind of the grammar. Is it acceptable to just write an expression without parentheses? What I'm asking is this VHDL expression, cat food, is assigned seals and, can I write that expression right there without parentheses? And the answer is no, but you wish you could. Even if it is no, it is recommended practice to go ahead and put those things in parentheses. The deal is VHDL won't allow you to do that. You'll run across as a syntax error. So you have to put those parentheses in there. You wish it'd be smart enough to realize that comes first, then that these things are done simultaneously, then you're ORing them together. It's not that smart. It's forcing you to go ahead and write those expressions so they're readable. So now what I can do is I can take that logical statement and simply put it in between the beginning and end. And because I want it to look pretty, again, it's a free format, I'm going to give a little tab in there so it's inset. Okay, so I'm going to go ahead and do that. There's our logical statement right there. In between beginning and end, notice I've inset it a little bit so I can know what's between beginning and end. And notice I've not put the parentheses in there. And let's say that's line 1, 2, 3, 4, 5 in a text editor. What you're going to do, and you'll see these things, I guarantee you'll get a syntax error. It's going to say syntax error line 4 next to or. And your job is to kind of interpret what is that compiler trying to tell me. Where is that syntax error? Well, it's telling you, hey, dude, put in those parentheses, okay? And even if it wasn't demanding those parentheses, put them in there. I know you don't need them, you think you don't need them, but put them in there so that way you can see what that expression is. Okay, well, let me prettify this here for you. There is our first architecture statement. It's actually a little bit even simpler than the entity. Okay, I just said you don't necessarily need those parentheses. I said you need those parentheses. I can tell you a way to get around those parentheses. And that's an area called the declaration section. And this is a major advantage of VHDL. The declaration section goes in between the architecture and begin. You don't need it, but it certainly makes your job easier. What the declaration is you're defining things internal to the architecture. Do you remember how your entity was just the inputs from the external? Here's our seals, our corn husks, and our mats coming in, and out comes cat food. Those are the only inputs, those are the only outputs to the outside world. What occurs inside here is the architecture. The architecture could have signals internal to itself that are maybe based off those inputs, but they're not accessible to the outside world. So that's what goes into the declaration section. And if you think about this, seals and husks, I could call that M. Seals and mats, I could call that N. And then I could OR M and N together to get cat food. Do you see what I'm doing? It's kind of that multi-level logic circuit approach. If you think about it, what this expression, seals and husks, or seals and mats, looks like, it looks like this. So as our input seals, it's going to both AND gates. So that is seals and husks. Here is seals and mats. What is that internal signal? That could be called M. That could be called N. What is this? M or N. So we're taking that multi-level look at these things. I can define an internal signal called M. I could define an internal signal called N, and then use them internal to my architecture. So let's go ahead and redo what we just did here and use kind of this declaration portion of the architecture statement. Give myself a little bit of space here. What I'm going to do is use this thing called signal. And the general format is what's the name of the signal, colon, so let's call that a acceptable name of the signal, colon, what data type it is. Notice it's kind of like the entity statement port where you got the name, the mode, and the data type. The signal does not have a mode, an in or an out or an in-out, because it's not an input, it's not an output, it's just used internal to this architecture. So kind of like it, slightly different. And remember to go ahead and put a semicolon there. So what I'm going to do is call signal M. What is it? It's a standard logic. Do the same thing for N. And there you go. So I've created two signals, M, which is a standard logic with a closed semicolon, signal N, which is a standard logic, close it. So now let's do our between beginning and end. Let's go ahead and do our expressions. Okay, and some of you guys might be concerned here when I write the following. Cat food is assigned M or N. M is assigned seals and husks. N is assigned seals and mats. And when I say alarmed, those individuals with a software programming background realize there's a problem in the order that I put those in. So cat food is assigned the values M or N. What's M or N? You know, if I was to do this first, this statement first, then this guy, I would have a problem because I'm getting the result first and then performing the intermediary steps second and third. You know, you don't build a roof to a house before you build the walls. You don't build the walls before you build the foundation. And that is the fundamental difference between HDL, hardware definition language, and software. Software is sequential, it's flow. We are defining the machine. We're defining a hardware that does this. These are concurrent. These are parallel, simultaneous. Any host of descriptions you might have want to use. They're all happening together. M and N are instantly defined as seals and husks, and respectively seals and mats. At the same time, M is being ORed with N. I'm defining a device that does that. And it doesn't matter. It doesn't matter the order you put these things in. I could put that down here, below here, like right in here, if I wanted to make sense of that. And so what I'm saying is use of these signals can substantially simplify the expression you're trying to write, and you could potentially come back and read this thing a little bit easier later on. Notice too, I don't have to worry about those parentheses anymore. And geez, what was my error? There's no plus here. You guys should have stopped me. You can't stop me. You see what I did there? There's no plus. I'm trying to. There's two different worlds. Writing it and then VHDL. Yeah, you'll probably catch me do that a little bit more often. What would happen? Syntax error. It happens to me too. Using these internal signals is not necessary, but it substantially eases it. Where do you put them? You put them between the architecture and begin. It's called the declaration section. Let's do another example of an architecture statement, kind of based off those previous entities we'd worked in the previous lecture. Okay, so if you remember our previous example 2 for the entity statement, we made a half adder where we declared input A, input B, output sum, output carry out. And what I'm doing right now, I'm giving you the expressions for sum and carry out. We'll worry about this later when we actually go into combinational logic functions. We'll actually derive those and see how those things work. And it's pretty cool actually. I actually like half adders and full adders. Kind of makes sense what the expressions are. Well, they all make sense. These ones are pretty easy to grasp. But so I'm giving you those expressions. Sum is equal to A exclusive ORed with B. Carry out is equal to A and B. What I want you to do is write the architecture statement. Okay, for the half adder. First thing, give yourself the skeleton, the basic skeleton for the architecture. And there's my blank skeleton, architecture blank of blank is begin end. Now all I gotta do is just put the stuff between begin and end. What matches these two things match? They gotta be the same name. I'm gonna call it ARC. Again, I have no idea why they make you do that, but you gotta do it that way. What am I gonna call it? Of half adder. Begin. What do I want to do? I want to say, I think our previous outputs were sum and carry. I can't remember what the text version, what we called them. Sum is assigned A exclusive OR B. Carry is assigned A and B. End architecture. Do I need internal signals? Do I need a declaration right here? Nah, probably not. I don't even know where you would use them in there. Probably wouldn't even. It's not going to make it easier to read. Let's go ahead and move on to example 3, which if you remember right was a full adder. Okay, so there is our full adder. That's our quasi-entity statement. It's got 3 inputs, 2 outputs, and let's say we called it A, B, CI for carry in, sum, because you can't write that actually, and CO for carry out. So the expressions for these guys, the sum is equivalent to the exclusive OR of A and B, the exclusive OR of CI. What does this mean? It's a simultaneous exclusive ORing of A and B and C, or it's the sequential A exclusive ORed with B, then exclusive ORed with C, which is saying this is equivalent to doing them all together, which is equivalent to doing this. That's kind of my description of a multiple input exclusive OR when it's odd, when there are an odd number of inputs. They all work. It follows the associative properties. We'll go into alternate methods of describing the sum. Carry out is equivalent to A and B ORed with A exclusive ORed B ANDed with CI into the carry in. Okay, so how am I going to go ahead and write these things in an architecture statement. So I'm giving you these statements. Go ahead and see if you can create, and you already did the entity. Let's go ahead and see if you can create the architecture statement for it. Okay, go ahead and start with your basic skeleton. There you go, there's my basic skeleton. I'm going to call this thing arc, short for architecture. What am I trying to build? I think we called it FullAdder. Okay, is begin. Put in your prettified tab there so you can see what's in between beginning and end, and just write the expression for sum. There you go. I'm calling these, by the way, A, B, C, I, sum, C, O. Those are the variable names that, let's pretend when I did the entity description, I called them A, B, C, I, sum, C, O. Do I need parentheses for this? No. I could do that. It would give me the same results. I could do that. It would give me the same results. What it's doing, it's simultaneous exclusive ORing it, and you're going to get an odd. It's high when it's odd. See if you can do the carry out. CO is assigned. Okay, and there is our statement in a very unpretty, very grammatically incorrect statement. Now your job is to figure out where do I put the parentheses. I mean, I've already got parentheses in here. Why not put a parentheses around that? Exclusive ORing of it. What is being ANDed together? Actually, let's just use different colors. That thing is being ANDed together. Finally, let's use pink parentheses and do that. Okay, so what I'm doing is I'm ANDing A and B. I'm exclusive ORing A and B. Then I am ANDing that with carrying in, and I am ORing them both together. See how pretty that is? Those parentheses make it readable. Hopefully you got the ability to go ahead and to do this architecture statement. Let's go ahead and see if you could potentially use internal signal assignments. So that's example 3b. See if you can come up with an internal signal declaration for that, and for that, and use these guys to create a new architecture statement which makes use of those internal signals. Okay, here is what I'm going to try. Okay, first thing is you might be able to do this just looking at the text version of it. You might want to go ahead and look at a multi-level logic circuit implementation of this. That being A and B. What is this signal here? It's A and B, which I can call P. What is this signal right here? It's A exclusive ORed with B, which I'll call Q. And finally, what is this signal right there in green? Well, it's CI ANDed with Q, which I'll call R. Okay, and this is my version of it. I know that you could have done several other ways. You don't have to call it P, Q, and R. But now go ahead, declare those signals in the declaration section. Okay, so the general format there is I gave myself a little indent so it can be nice and pretty. I'm going to say signal, what the name of it is, P, colon, what type of data it is, put a semicolon. Now I can use P inside my statement. Which one is P? It's this guy right there. Okay, so what I can say is P is assigned A and B, semicolon. Replace that with a P. Go ahead and see if you can do Q by yourself. Okay, so there's my signal declaration for Q. It's a standard logic. Where is Q within our circuit? It's right there. So I can go ahead and replace this guy with Q. As long as I define Q is assigned A, exclusive ORed with B. And the astute among you may realize that Q is used again somewhere within our architecture statement, namely right there. So I can go ahead and just replace that Q right there. Finally, we want to go ahead and develop the statement for R. And go ahead and see if you can do that. There's R right there. And what is R? R is assigned Q ANDed with our input CI, semicolon. So I can replace this whole thing with R, semicolon. Do you have to use internal signals? No, you don't. Does it make your expressions easier to troubleshoot at the end? Yes, it does. So I'm going to go ahead and clean this up. It's very easy to see what is happening here within the individual architecture statement. The other thing too is you may save yourself some time by doing these declarations in a single line. Because what I can do, I've got P, Q, and R all taken up a separate line. I like it this way. I'm clearly seeing I've got 3 signals. You can save yourself space, P, comma, Q, comma, R. Do all declarations in a single line if you want to do that. I wouldn't recommend that because now I see a single signal declaration, but in reality there's actually 3 there. I don't necessarily like that because I want to know that there are 3 internal signals. Some of y'all may be kind of overwhelmed about these entity statements and architecture statements. don't worry. This is the first time you've done it, the first time you've even seen it. You haven't even had a chance to actually write these things. How do you learn VHDL? You learn it the way I did it. You learn it by writing it. If you're thinking, hey, I'm going to quiz you guys on these things, don't worry about it, guys. I'm not going to quiz you on what is the exact statement. I'm not going to do syntax, at least for this first version. Once you do it a couple of times, yeah, I'm going to start quizzing you guys and testing you on these things. But you need to actually do this yourself before I can start quizzing you on these things. I may ask you a question, hey, what's the difference between an entity statement and an architecture statement? What is an acceptable variable name? What is not an acceptable variable name? Something like that, that general knowledge about this. What is HDL? What's it trying to do? A PLD, what is a PLD? That's all fair game. All this syntax stuff, it comes with time. And you're going to see me make some syntax mistakes. Secondly, some of y'all may be like, why are we doing this? Why are we learning this stupid computer programming language when I want to learn about digital electronics and learn about control of motors or whatever? Just check this out, guys. This has applications. And the simplest application to begin with is just that Happy Cat cat food factory. Go ahead and erase this and just get our entity statement back in there. Just a real quick example why you use VHDL, why you use PLDs. Okay, so here's the whole thing put together. We have our entity statement from our previous lecture, and I think I called it factory, the last one. I think so. Let's just call it Happy Cat. The entity Happy Cat, what is its inputs? Got seals, husks, and mats. They're all inputs. It's going to take cat food, that's its output, and what's the architecture of it? The architecture is the following right there. You got two internal signals, M and N. They're both standard logic. What I'm going to do is begin it, say cat food is M or N. What's M? It's seals and husks. N is seals and mats. And then N. Pretty simple. That's what we've done thus far. Now, imagine the PLD version of this thing. It's a black box. You got inputs, 3 inputs, seals, husks, and mats. Output cat food. It's just some relay device. It's not actually spitting out cat food. And we'll actually discuss how to apply these things to motor control a little bit later. It is a simple, stupid example. Totally stupid, but you're going to remember it. It's a single device. Try to do this with a fixed function. So what is the expression? It's M or N. So we're going to have an OR gate, 7432. It's seals and husks. We're going to have a 7408. Seals and mats. We're going to have another 7408. And what I'm going to say is a quarter, quarter, quarter. Do you remember what those quarter notations mean? It's meaning it uses 2 AND gates of a 7408, so half of a 7408. So when I parts list this thing out, I can tell how many 7408s it is. So that's a pictorial representation of a fixed function device. What does it actually look like? And that's, by the way, that's seals and husks, seals and mats. You still got 3 inputs, seals, husks, mats, and cat food. What does it look like to wire up? What does that one look like, the PLD? It's 3 inputs into a black box and an output. Here's our fixed function. That's what the circuit description look like. How does it look like to wire up? Well, you take a 7408 and a 7432, time both to +5, time both to ground. Where's S, H, and M? S is going to the input, and H is going to the input of one AND gate. The output of that is going to the input of the next OR gate. That's what I'm talking about is red, blue, gray. Okay, what's going on now? S is going to another input of an AND gate. M going to the input of another AND gate. The output of that is going to the input of an OR gate. Finally, what do we get for our output? This guy right there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 wires. 4 wires. 2 devices. 1 device. All of a sudden, something comes along. Maybe the government. And the government says, hey, Happy Cat, we don't want nuclear waste inside our cat food. It's illegal. You cannot have nuclear waste inside our cat food anymore. You've got to change your logic circuit implementation to go ahead and account for no nuclear waste, i.e. not nuclear waste. How easy do you think it's going to be able to change that? How easy do you think it's going to be able to change that? What do? I change the entity statement. I add in a nuclear waste detector. I change the architecture statement to account for the new logic. Boom, it's done. how do I do this? I have to add more gates. I have to add more physical wires. Do you see what PITA that is? Pain in the versus a fixed function versus a PLD. This is akin to that transition from relay logic, i.e. ladder logic, to PLCs, which you'll be learning about a little bit later. And I am going to go into how these digital electronics principles are applied to motor controls and PLCs. The PLD, the programmable logic device, that's kind of like the PLC, programmable logic controller. I've got inputs. I still have to have 4 inputs. Seals, husks, mats, nuclear waste detection, and I've got to go ahead and have a single output there. I still have to have those inputs, but how I structure those things, I can program. I can reprogram. Whereas the motor control, i.e. the ladder logic or relay logic, or the fixed function version of it, I've really got to put those devices in there. I've really got to wire those things up. So let's go ahead and do just a quick example. Let's change the expression. And I'm giving you the expression right now. We will learn how to actually develop these expressions a little bit later. Okay, so now the new expression that we want to implement is cat food is equal to seals and husks and no nuclear waste, or seals and mats and no nuclear waste. What does this look like from a multi-level circuit perspective? And there you go. So you've got seals ANDed with husks, ANDed with not M, ORed with seals, mats, not M. And that is, by the way, right there. That's the ultimate expression of that. Look at what we have come up with here. It's more gates. We had to add a NOT gate. So pull out the 7404. Add that to your parts list. Oh my gosh, we're not using a 7408 anymore. We're using a triple input AND. Maybe I could save some money by using the associative property of 2 input AND gates, 7408s, by making a 3 input AND gate from 2 nested ANDs. What I'm saying is do something like this. That's equivalent to a 3 input AND gate. You guys should remember that from associative property. Oh, and then a 7432. Yeah, I saved some money there, but I'm maxing out the 7408. I've used up every single gate on that 7408, and I've added a new 7404. And this one's got power, that one's got power, this one's got power, that one's got ground, that one, actually these are the same gates. Excuse me, this is all in the same 7408, 7432, 7404, but power, ground, power, ground, power, ground, connection, 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 connection. And if we're going to save some money by using the associative property, connection, connection. That's a lot of wires. Now, compare and contrast to what I'm about to do right here. Entity, add another input. Architecture, change the expression. Download, blink, it's done. And there you go. I've made the modifications to that. What have I done? I've added an input, nuke, and all I've done is I've ANDed a not nuke, ANDed a not nuke. I still have to connect nuke to a pin, which we'll go over into the actual implementation of these things, but 1, 2, 3 lines in code versus rewiring new parts and all the pain associated with a fixed function circuit. So this is the reason why PLDs are being used more and more prevalently. It saves you time in the actual implementation of these things. You can always upgrade and repair and change these things. As long as they're a reprogrammable device, the sky's the limit. You can reprogram these things as many times as you wish. Okay, this kind of concludes the VHDL architecture statement. I did go a little bit further than I intended to. We actually kind of tied these things together, but now we're actually going to go ahead and implement both the entity architecture in combination with the library statement, because that's the third thing that's inside of VHDL, because the third thing up here, if you can imagine up there, that's our library. We'll go into that and we'll actually go ahead and implement one of these things. And this is really kind of the point where you've just got to go ahead. This is portable. This whole thing is portable. This VHDL statement is portable. The whole thing. I can go to Altera, I can go to Xilinx, I can go to any particular device manufacturer as long as it fits on the device and send this to that device. With the actual implementation of these things, the actual placing and routing and programming of the device, that's when it becomes manufacturer specific, and you're going to have to use that manufacturer's software, and you're going to have to assign those pins. Alright, so we'll go into the implementation of this Happy Cat factory.